We have learned how to determine work done using an equation or using a graphical approach. For equation, we will use the scalar product of force and displacement, which is F dot S. For graphical approach, we have an F parallel against S graph. So from this graph, we determine the area under the graph, and that area under the graph will represent the work done by that force F. Now we have known all these things, so let's try and take an example that we have over here and analyze everything that we know about work done. In other words, we'll try to determine the work done by the various forces that are acting on the body. So we have here a 5 kg body, and this body is lying on the ground, and he has an handle which is angled at 30 degrees above the horizontal. Now if I apply a force, external force of F of 50 Newton along this direction of the handle, then you see an external force like this. So because of this external force, this object here will experience a displacement which is 10 meter to the right. This is an example. It's 10 meter to the right, it moved to the right for 10 meter. So, and we also include a situation, make it slightly more complicated by saying that this surface is rough and the coefficient of kinetic friction is 0.20. So this is quite it's not a very easy, straightforward situation. So we'll try to analyze what are the forces acting on the body, and for each of the forces that we determine, we try to see whether that forces do any kind of work on the body. So if you draw a free body diagram to illustrate all the forces acting on the body, we will see that this object has mass, therefore it will have a weight. Then after that, we also learn that this object here, because there's a force being explicitly mentioned here, you should have an external force angled at 30 degrees above the horizontal. And after that, you see that this object here is touching this surface, therefore there should be a force perpendicular to this surface, which we call it as normal force. And this normal force will be pointing upwards. And lastly, because this object is sliding across the ground to the right, this block here should experience a kinetic friction in the opposite direction to the direction of sliding. So you should see a kinetic friction pointing to the left. So this free body diagram here illustrates all the forces that are acting on this body right now. And actually we can find whether all these forces are doing any work or not on this particular body that we have here. This particular body moves 10 meters to the right. That's the displacement that happens with the body. A body can only has one displacement because that's one body, one displacement. But for that one displacement, there are multiple forces acting on the object at the same time, and each of the forces contribute different amount of work done towards this object undergoing displacement 10 meter to the right. Okay, so we'll have to determine the magnitude of the forces for the external force, the weight, the normal, and the kinetic friction before we move on to study what are the work done by all these forces that we have here. So the force is given here, the external force is given here as 50 Newton. That's the magnitude. Let's find the magnitude of weight. So for weight, we know it's just a usual m times g, mass times the acceleration due to gravity. So your mass is 5 kg times 9.81, you get 49.1 Newton. So this will be the weight of this 5 kg object here. And this force is exerted by the earth on the object. The earth is pulling the object. Okay, so next you have your normal force. For normal force, how do you determine the normal force? You have to apply the concept of Newton's first law in analyzing the y dimension that we have here. We know that this object here will not be moving upwards or will not be moving downwards. Initially, it is at rest at the y dimension. After the whole journey, it is still at rest in the y dimension. It is moving in the x dimension, but in the y dimension, it doesn't move up, move down. So it is at rest and remain at rest in the y dimension. So the sum of F in the y dimension should be equal to 0. And as you can see, in the y dimension, you have your normal force pointing upwards. Then you also have your y component of external force pointing upwards as well. That's why you add on F sine theta. This F sine theta here represents the y component of the external force. Then you also have your weight pointing downwards. Therefore, you minus the magnitude of weight. This N, this F, and this W here are magnitude. So all these things should not have any sign. You put the sign outside here. Then this is equal to 0. Then you move around because your subject is normal force. So you put normal force on the left hand side. You put everything else on the right hand side. You change the weight into mg. And you perform your substitution. So mass 5 kg, acceleration due to gravity 9.81, external force 50 Newton, and the angle above the horizontal is 30 degrees. So after substituting in everything, you'll find the normal force to be 24.1 Newton, and that will be the magnitude of normal force. Lastly, you have your last force, which is the kinetic friction. For kinetic friction, since you have obtained the normal force, and you also have the coefficient of kinetic friction given to you, you can just determine the kinetic friction, the magnitude of kinetic friction, using kinetic friction equals to mu k times n. So you can just substitute in mu to be 0.20, normal force to be 24.1, and you get 4.81 for your kinetic friction. So these are the magnitude of all the forces that are acting on the object right now, as we can see in this free body diagram right here. So I'll keep this free body diagram, I'll keep what I have here, and I'll use the forces, the magnitude of the forces that I have here, to determine the work done by these various forces. So let me move things around a little bit. So I have my free body diagram from earlier. I have all the magnitude of the forces that I have determined just now. And I put here the displacement 10 meter to the right because it is not shown in the free body diagram and it's not given the value here. So I'll use these three sets of information here to determine the work done by these various forces acting on the body. So let's start with the first one, the work done by the external force. So if you are calculating a work done by the external force, again, since all these forces are constant throughout the journey, we say it's 50 Newton and we never say it changes throughout the journey. So this is a constant force. This weight here is also constant. As long as your mass doesn't change and it doesn't fly away from Earth, then your weight will never change. The normal force, as long as you stick to the surface, then that will be the normal force unless you exert another kind of external force. For friction, since the normal force is fixed, your mu k is fixed, so your friction, kinetic friction here will also be constant. So all these forces are constant and they never change throughout the journey. So because they never change throughout the journey, you can calculate the work done using equation and you don't need to resort to a graphical approach to solve the problem. So let's find the work done by the external force. You can just find it using F times S times cos theta. Label a subscript F here to show that this angle is specific for this external force. And I label W F here to show that this is the work done by the external force. Putting a subscript can make everything clear because there will be multiple W's over here. You have your W here, you have your W here. So it's good to label subscript to show clearly what are you calculating. So you can substitute in your F, your S, but for the theta, you might need to check. So how do you check? You place the vector of F and the vector of S, you place their tail on a common point. So F and S now share the same point as their tail. So from there, we see the angle between F and S is 30 degrees. So we can substitute 30 degrees for our theta over here. So let's do our substitution. We put 50.0 Newton for the external force. We put displacement 10 meter for the displacement and cos 30 degrees. And you get our answer to be 433 joule. So this is the work done by the external force on the body that we observed just now. Okay, but we still have other forces acting on the body, and all those forces also contribute different amount of work to the body itself. So let's try and look at the second one. We have the work done by the weight. So work done by the weight. Well, you might think the subscript is W, subscript W. Well, it's not wrong to write W, subscript W, but there's a lot of W. So I think changing it to a G might be more appropriate because G usually we stand for gravity, right? So it's still clear what you are trying to say. So this is work done by gravity and it's equals to mgs cos theta. So it's Fs cos theta, but the force here is weight, so it's substitute in mg straight away. I don't put in W because there will be too many W, then it will be quite confusing. So I just write mg, then times S times cos theta. But for this data, I label a subscript G to represent that this angle is specific for gravity. So it's different from the angle that we have for external force. So how do we check it? We bring the weight to this point, share the same point as the tail, share the same point to put their tail. Then you see that the angle between the weight and the displacement is 90 degrees. So now this angle that we substitute here should be 90 degrees. So let's do our substitution. So mg here will be 49.1 because mg here is weight. then tan is the displacement, then cos 90 degree, the 90 degree represents the angle between the force and the displacement. So we know that cos 90 degree is equivalent to 0. Cos 90 degree is 0. So your answer here will be 0. So what does this tell you? It tells you that the gravity does no work on this body when this body is undergoing a displacement 10 meter to the right. Okay, you can call it this gravity here, this weight here is irrelevant to the displacement going to the right now. Okay, so let's move on to the third work done. This is work done by the normal force. Again, we'll do it using similar method. Work done by normal force is equals to the normal force, the F. The F right now is normal force, the displacement, and cos theta. By subscript n because this is the angle for normal force. So now I substitute in n for 24.1. Oh, before I substitute, yes, I bring in the normal force to put it over here. Then I check the angle between the normal force and the displacement to be 90 degree. So knowing the angle, I can just substitute everything. N is 24.1, S is 10 meter to the right. Then the angle here, I substitute in 90 degree. So cos 90 degree again is 0. So because you know it's 0, the work done by normal force will be 0 joule. So this normal force here does no work on the body when the body moves 10 meter to the right. Okay, then now the fourth forces, which is the kinetic friction. Let's determine its work done. So the work done by kinetic friction, again similar method. The work done by kinetic friction is the kinetic friction, a force F is the force, but now it's kinetic friction times displacement times cos theta, but this theta is specific for kinetic friction. So let's bring the friction over to this side. Then we see that the angle between the force and the displacement is 180 degree. They are in opposite direction. So opposite 180 degree. So when you substitute in your kinetic friction as 4.81, displacement as 10 meter, and cos 180 degree to represent the angle between the force and the displacement. Cos 180 degree from a trigonometry, you know that it will be equals to -1. Therefore, you know that your work done here will be a negative value. So negative 48.1 joule. Okay, we mentioned earlier that work done it's a scalar quantity. So when it's a scalar quantity, it means it has magnitude but no direction. So as you can see here, I didn't include any direction for my answer of work done. But you can also see here that work done can be positive and it can be negative also. So scalar quantity, because it has magnitude only, it can be positive or negative. If you're wondering, I heard before from somewhere that magnitude should always be positive. No, that's incomplete. The magnitude of a vector must be always positive, but a magnitude can be positive or negative. Okay, magnitude of a vector only it will be always positive. But for this case, it's a scalar quantity, it's not a vector quantity. So this magnitude here can be positive and negative. And in the next video, we will try to understand what does it mean when our work done is positive, what does it mean when our work done is negative, and what does it mean when our work done is 0.